It's trying. Okay, there it goes. Okay, I think we can start officially. So what was that question that you were referring to, Summer?
It's problem 15 on percent 15.
Gotcha.
Over 15.
Problem, is it section 5.4? Gotcha. Or if you like, you could just read out what the question is. That might be a little bit easier.
X equals the interval from 1 equals to x ln t.
From, you said it was 1 to, gotcha.
And then ln t.
Okay, awesome. And we're probably differentiating it. Does that sound about right?
Yeah.
Gotcha. Did you have a specific question on this one or more just about getting started with it?
I'm confused where to start, and then I'm also confused on how to go from 1 to e.
Mhm.
Because it's asking you part 1 of my language is called
Right.
Start with that.
So part 1 of the fundamental theorem, let's do a kind of an easier question on that one, just to get a feel for it. Let's define a function that goes g of x, integrate from lower limit of integration. I'll put a 0 here just to make it different. Let's go up to x. Now it's a nicer problem. And it could be pretty bad looking stuff here, like cosine cubed t plus 1. I have no clue how you'd integrate this kind of thing. This one might have to be numerically approximated. But if you're differentiating it, g prime of x, I like to put in this step to visualize what's about to happen. G prime can be thought of as d by dx of 0 to x root cosine cubed t plus 1 dt. So fundamental theorem of calculus part 1 says, if you differentiate a function that finds the area under that curve from 0 to x, what you get is this stuff, exactly the way it's written, except for one change. If the variable is x to start, the variable stays x and goes cosine cubed x plus 1, and now your work is done. Does that make sense there on using the fundamental theorem part 1? Gotcha. Same kind of thing happens here, except this one turns into a chain rule. The input is x on both of those functions. But if the input is more than just x, that's an inner function that you have to handle second. And so upon differentiating this one, h prime of x is going to be the derivative with respect to x, 1 e to the x, natural log t dt. And let's copy the approach that we did from before. First thing we have to do is take what's the integrand, switch the variable. Well, let's write it out like this. Natural log of something, and then just about every single time we did chain rule, we multiplied by the derivative of the inner function. So it'll come in like this to start, and I think a new color is definitely a good idea here. Then we take that inner function, we'll go both here and here. So last thing you have to do is differentiate this one. Not too bad, right? Just e to the x. Natural log with e to the x will cancel, just leaving an x. And so this one simplifies pretty quickly, not too much work after that step. But does that make sense on getting through that one there?
Yeah, I was trying to complicate it.
Yeah, this one's weird because chain rule, it just feels weird for this kind of function. But if you identify the inner function, that's pretty much the process on this one. Well, other questions, folks, to start us out today? Okay, thanks for asking about that one. We use the fundamental theorem part 2 so often that it's really easy to forget the fundamental theorem part 1 that we just took a look at here. But let's return to the Moodle website. I don't have a ton of announcements other than, let's see, we had to take an extra day off returning from the break, but we have a shiny new projector. I think that's great. I've been complaining about it for a while, except when they installed it, they didn't configure it right. It just was not working. If you came into class on Monday, it looked like we were having a raid in here, but that way it was flashing. constantly. So after losing a day, I felt like probably the best thing we ought to do is, I already indicated I want to do more problems here after returning from the break. So that's what we're about to do, practice 5.5 more. Then I'm going to consider section 6.1, 6.2 as potentially the last couple sections of the entire semester. Chapter 6 is really just getting extra practice on integration. So we can go as far as we have time left for, but I don't want to try to race through these topics and lose review days. So 6.1, 6.2, we should be able to cover in decent order. We might finish 6.2 when we come back on Monday. Then we might take a look at section 6.3 on Wednesday's class. And that saves all of Thursday, December 7th for reviewing for the upcoming final exam. So that's the plan so far. Any questions at all about that so far, folks? Yeah. It is 8 to 10 p.m. They kind of mess us over with that. They figure if it's a night class, then that's a night time and they just throw it at us. It's a rough time that they give us. I have another class that goes from 6 to 6:50. They also threw that class into the same time slot. So when you come for the final exam, you'll see some unfamiliar faces. That's just the statistics class before us. So sorry about that. I know that is a horrible time. If that's going to cause a major problem, send me an email and we'll work something out. Other questions about that so far? Okay, and this is actually, as awful as it sounds, that's a traditional time. Every semester that they've ran this class on this campus, final has always been from 8 to 10 p.m. I don't know of any exceptions, and not, at least not on my end. And one of the ways I compensate for that is when I go to actually give the final exam, here's some of the old ones from the past. This is the one exam that I do curve. I don't think I have ever curved exam 1, 2, and 3 in this class. But when I give the final exam, I know it's a rough time to do it from 8 to 10 p.m. We're not at our best at that hour. Heck, it's hard to do math at 7 p.m. already as it is. And so that's the exam I do try to curve. Essentially, when I write a final exam, this is my goal. I'm trying to write an exam that's going to encapsulate the whole course, give problems representative of pretty much everything that we did. But I'm not trying to write an exam that's going to change people's letter grades. So after grading them, I look at what happened to the course average. If the course average dropped by like 5%, I curved the exam a little bit to return it to about where the class was on average. So the final exam is not meant to drop us our grade on average. It's meant to just be formality because the math department says we must do it. So that's what we're doing. Sorry for the horrible time the registrar threw at us. Other questions about that so far? Yeah. Yeah, absolutely. I believe I have one I'd have to get with you if we make arrangements. I'm giving another exam. I think it's from 3 o'clock or 3:30 on the same day. That's a much nicer time. I agree. Yeah, send me an email and I'll be very happy to accommodate that. Okay. One thing I would mention though is this has happened to me in the past. If you change your exam time, just make sure I give you the right exam. Sometimes I get just a little mixed up. I've accidentally given a student a little wrong final exam on finals, and that's a really bad experience for everybody involved. Other questions so far though? Okay. And while we're talking about the final exam, I wrote out this blurb right here as just some advice on studying for a final exam. Essentially, the idea is if you're trying to get better at something, let's say it's crochet. Really, the only way to get better at crochet is you have to crochet, loads of it. Probably what we're thinking of is we want a good score on the final exam. And really the best way to get a high score on your final exam is you have to take one of these and study it as if it was a real final exam. I put down a set of steps here, but just to paraphrase, if you took this exam, clear out 2 hours in your schedule. I know that's pretty hard, but do the best you can. If you have to break it up in 20-minute, half-hour segments because life is that way, that's okay too. But clear out a time slot as 2 hours would be ideal. Give yourself some things like, I'll say, make sure you have, I went for 3 on that class. Jeez. Make sure you have your notes available. Have a calculator like the TI-30X2S available as well. And solve this with nothing else in front of you. Don't look at the solutions to the exam. Don't look at your book or any other notes. Only use the materials that you yourself are really bringing to the final exam. Then it might be kind of tough, especially the first time you did it. But now you're studying the final exam in a way that you will really take the final exam. That's really the best way to study for any exam, really. At the end of the 2 hours, then just stop, take a look at the solutions, grade your exam, and circle anything that you felt like, well, I didn't do quite right, or I wasn't sure how to do it. Those are going to be the areas that you need to return to the book and study a little bit further. And if you're not sure what section a problem came out of, just email me, say, hey, Mike, I'm on the fall 22 final exam, problem number 3. What area of the book should I study to get a better feel for problem 3, part A? I'll always be super happy to help out with that kind of information. I'll target the right section out of the book and out of the notes. So grade the work after the 2-hour segment using the solutions that will be provided shortly, and you'll know exactly where to study. Then rinse and repeat. There's other exams as well to try multiple times. Other questions about that so far? Yeah. It's going to go through 6.3 so far, yeah. And that means some of these exams, they're going to have problems that are not on the real final exam. I'll put a little notes here that says, when I go through these and post solutions, I'll say stuff like this, exclude problem so-and-so, so you know which one is we didn't get that far this semester. Other questions so far? Okay, so, sorry, go ahead.
With the final exam, basically lower scores, is that all of your exams with lower scores, or is that just one?
Just the one, yeah.
Okay.
Mhm.
It's good because it's funny, so I wonder.
Yeah, let me take a look at my writing there. If your final exam score is larger than the minimum score among exams 1, 2, and 3, the final exam will replace that minimum score.
Okay.
Yeah, referring to just the one. Those are good questions so far. Other questions at the moment?
Other than good.
That's this one. Oh, where did I put it? I think it's up. This one here. Thanks for mentioning that one. I think I was about to forget to even mention that in my announcements. The way to do this extra credit opportunity is right or left click here to open up this stuff. Your course evaluation is right here on this link. And it's just a really short, I think most people are finishing this around 5 minutes. I think they say take 15 minutes to do it, but it's a pretty fast evaluation. After you answer all the questions, there'll be a page that says, thank you for completing the course evaluation. Either take a screenshot or a picture and just email it to me, and that will be you completing that extra credit there. Make sense so far? Awesome. If you've already done the evaluation, then good on you, you're ahead of the game. But you still did lose the opportunity for the extra credit. If your evaluation is done, just come back here, click again. I'll tell you you've already completed the evaluation and then send that to me. That works just as well. So what will happen with the extra credit, now that we mentioned that?
And then is it actually 4% of a drop, or is it 3?
3 for the moment, and this one will take us to 4.
Okay, so the 3 drop?
Oh, 2. Jeez.
Or maybe I'm sorry.
I might have misremembered.
So it's 3 and then 4 is in the complete that?
I'm not sure at the moment. Let me take a look. It says
Oh,
here,
it's 3.
lowest 3.
I can't read.
You know, these PDFs are tricky. The level of zoom you change, sometimes weird
Yeah.
artifacts appear, especially on a cell phone. So that could have been what happened. So yeah, if you complete that course evaluation, I'll change it to dropping, where is it again? So much on the website at the end of the semester, to 4 homework assignments dropped, the minimum 4. Yeah.
Just
Oh no, this, let's see, Mike Jabo-san. Thank you for pointing that out. Let's see if we can fix that right here. It should be. You think I knew how to spell my own name? Thanks for spotting that. Mike Jacobson. Oh, I got to fix that in my other Moodle pages, but I'll come back to that later. Okay, so that's our extra credit opportunity so far. And we had other stuff. This one is still on the table. The final due date for any homework assignment, whether it's a redo or if you had a late assignment you did get in, you can still complete that. The last day to complete all assignments will be December 11th, the same day as the final exam. We could say if we want a time 11:59 p.m. or something like that, you can send these through to email and that's still just fine as well. So whether it's a revision, a late assignment you didn't get to, I'm still collecting those. It wasn't just for the Thanksgiving break. And I think I ran out of announcements, but are there questions or comments so far, folks? Okay, well, let's take a look at section 5.5 again. I definitely want to solve at least a few more problems since this is a really, really important section to get us into calculus 2. Then we'll take a look at section 6.1 after we complete our review here. So first problem to take a look at will be this thing. Let's remind ourselves of the instructions first. The instructions said at the very top here, evaluate the definite integrals. We're still using the substitution rule, and so the process is going to be pick a u, so we can change it to f of u du in our u substitution. Then take your limits of integration, take b, run it through g of u, and get your g of b, and we'll change the limits of integration as well. So that's going to be our process. It looks like a lot's going on, and you know what? I think there really is a lot going on. But if you look at each individual tree instead of the whole forest, it's really not so bad. So let's take a screenshot here and start this off fresh. It's been a long break, so it's definitely worthy to come back here and practice a few more, I think. So that's the theorem we're going to use. Really, all this is fundamental theorem of calculus combined with the substitution rule. I want to start off by solving this weird problem down here. We want to evaluate the definite integral from e to e power 4 of that wild function, and there's no way I could really come up with an antiderivative unless we break it down a little bit first. We're looking for a function u. Often a good choice is u should be some function that looks like it's inner to something inside here. Anyone spot what looks like a good inner function? Yeah, I would agree with that. Natural log is inner to the square root function. And if you differentiate natural log x, you would get a 1 over x. 1 over x isn't a problem, so it looks like we're on the right track with natural log x right here. So u, let's set as ln x. This starts our u substitution. The immediate next step we take is form a differential. But you know what? Just because there is a lot of steps on this, let's put down a sequence of steps. Step 1, we would do a differential, or excuse me, we would do a substitution. Step 2, we calculate its differential. It'll be du equals. Now here, we're taking the derivative of natural log x. That gives us a 1 over x. And then we throw a dx on it, since the variable was itself x. Looking at the integrand again, here's 1 over x dx. That means we're in business. Everything here is accounted for. Nothing is left over after using u and the du substitution. But even though it looks like everything is going according to plan, sometimes people find that this is still a pretty helpful step. I'm going to rewrite this as integrate from e to e power 4. We'll change those limits in the next step. And then rewrite this as 1 over square root natural log x times 1 over x dx. I haven't achieved a lot here. It's all just straight up organization and nothing else. But sometimes in mathematics, organization is king. 1 over x dx placed together, it's just more clearly going to turn into a du. Then 1 over root natural log x, we knew that's going to be a 1 over root u. And so now we're just about there. One last thing we need to take care of is limits of integration. Any questions, folks, before we go to that next step? Okay, I would consider this to be worthy of step 3 in its description. What you want to do is carefully organize this. The upper limit is e power 4. The lower limit is e. As silly as it sounds, it's a good idea to write it in that order because we're going to change those in a systematic way by essentially feeding these values into the u function. So u becomes natural log e power 4. And the lower limit for the new integral is going to be natural log of just e. And this is all really, really rigged. This right here causes a cancellation, natural log with base e, and we just get a 4 here left over. Cancellation would look like that. There's a cancellation on this one, but sometimes not a bad idea to put a power on your e, because it's not like everything disappears. When you cancel, you get a 1 on this one. So that's our lower limit. That's our new upper limit. We're integrating from 1 to 4 now. This means we won't undo our substitution. You have the right values for the new variable u itself. The integral is now 1 over root u, where natural log x was. And the whole 1 over x dx, this portion, is just going to turn into du. Does that look all right to folks so far? Okay, so this, let's call this step 4, where we actually made the full-on substitution. And everything we do out from here, it's just the conclusion now. We're finishing off the integral. This will be our step 5. Well, in our step 5, I wouldn't want to integrate that thing. That's pretty rough to deal with. We want to change the exponent here. The root is really a power of 1/2. But we're going to bring it up to the numerator, so it becomes u power negative 1/2 altogether. It's not a big change, but this perspective just makes it much easier to deal with. Does that look right to folks on going from 1 over root u to u power negative 1/2? Okay, next thing we're going to do is integrate that. Add 2 over 2. We're adding 1 to find its antiderivative. So now it's going to be power 1/2. We multiply by the reciprocal of 2 over 1, or excuse me, 1 over 2, which is 2 over 1, or just times 2 if you prefer. Then I've only one term. We can associate just u power 1/2 and leave the 2 factored out. We'll evaluate from 1 to 4, the new limits of integration from before, and we're pretty much done at this stage. We just have to go through the last motions. 2 over run, we can write in as a 2. For u power 1/2, I'm going to go back to the square root, since that's just more visually easy to work with. This will be square root of upper limit 4 minus the square root of the lower limit 1. From here, we can still calculate and get 2 times 2 minus 1 after taking both of those roots. Just keeps on going. Now it's 2 times 1. And so the exact area under this curve is now found to be 2, just a dead-on 2 somehow, some way. So that's the process, folks. I think the hardest part about this is finding u, formulating its differential, and then rewriting to this step. But once you get to this step, pretty much this is what happens. We're taking a problem that's pretty hard, section 5.4. We're not settling for doing a nasty problem like that. And so all these steps, their whole purpose is to take us to section 5.3, when we first looked at the fundamental theorem of calculus. And even in calculus 2, that's the strategy. Take something hard, reduce it way down with the right substitution or the right method, so that it looks like one of these problems from the past. Well, we ought to try a couple more, but any questions at the moment, folks? Okay, so let's go off to now part D, just for the extra practice. And for part B, let's work on this thing. Let's pick out a good one. Let's integrate from a lower limit of pi over 6 to pi over 2. And let me move that out of the way. That's is very distracting when it's blinking like that. So from pi over 6 to pi over 2, let's deal with cosine theta divided by sine cubed theta d theta. So that's our whole problem right here. Looks like it deserves a new page. Let's drop it down. First thing we need is definitely a good choice for you. Any volunteers for what ought to be chosen this time? Let's go with sine squared theta. Awesome. With a sine squared theta, next thing we have to do is get its differential du. And this one will be a chain rule. Differentiate as sine squared. First thing that comes down is our 2. We'll have 2 sine theta here, multiplied by sine theta prime through the chain rule, and then a d theta. So this will simplify down to du equals 2 sine theta cosine theta d theta. So if we go with a u equals sine squared, we'll be left with this sine down in the denominator right here, and we'll have a cosine to account for, but it looks like we're possibly in a little bit of danger with this one. We have to deal with a sine theta cosine theta in the numerator, but our numerator just has cosine theta d theta. It's missing that sine theta. We could possibly insert it, multiply above and below by sine, you get sine squared down below, and that might make this one work. I'll leave it up to the class. I'm not too sure if this one will work. It might just work, or we might have to do some algebraic manipulation. Should we give it a try and see what happens? Let's go for it then. Awesome. So first thing I would do then is get rid of the 2. The 2 is not a problem. We'll just divide both sides of that equation by 2 to get a 1/2. Du equals sine theta cosine theta d theta. So for this substitution to work, all of this quantity here must be in the numerator. We have a little bit to start, and here's how we can proceed. We're going from pi over 6 up to pi over 2. If we need a sine theta, we can try multiplying it above and below. So let's go cosine theta, sine theta. Then down below, it's now going to be sine to the power of 4 theta with a d theta on the end. So that's how it starts. Now let's take a look. Sine theta cosine theta d theta is all of this right here. So we definitely can substitute that out. Next thing we have is u is equals sine squared, and that works out because the power is right. That's just going to be a u power 4, excuse me, a u squared there. In other words, if u is equal to sine squared theta, then u squared is sine power 4 theta. So this substitution will work. We just need to feed pi over 6, pi over 2 into the original u there, change our limits, and we'll be all set. Any questions, folks, with this one so far? Oh, what I did on this step right here was I multiplied by sine theta. That's this one that was extra right here. Then I multiplied by sine theta again, just to balance and not change the equation. And so that made it go up to sine power 4 right there. Or maybe seen a different way. On this step right here, pretty much just took the original thing, cosine theta. Oh, sorry about that. Cosine theta over sine cubed theta. And we noticed we have a need for sine and cosine in the numerator. So in this numerator, we just multiply by sine theta. We have to divide by sine theta, so now we're just multiplying by a 1, d theta, and it turns into pi over 6 up to pi over 2. Cosine theta, sine theta over sine power 4 theta, d theta. So that's what got us to that step there. Does that make sense so far? Awesome. Other questions or comments at the moment? Okay, so taking all of this right here, that's going to just turn into 1/2 du. Sine power 4 theta, that's just going to turn into the u squared right here. So last thing on the table is we'll just change the limits of integration. So let's go through the motions. The variable here is theta, so the way I would start this step is by writing theta equals pi over 2. There's our upper limit. Theta equals pi over 6. That's our lower limit. Then transform this into a variable for u. U is now going to be sine squared of the first thing, pi over 2. Then down below, u will be equal to sine squared of the second value, pi over 6, the lower limit of integration. Now we just have to do 2 trig evaluations, not too bad. This is all at pi over 2, so a trig wheel on this thing, if we wanted to see one, would look about like this. So first value is up here at pi over 2. Second coordinate is going to be 1. We also have a pi over 6, so we should probably put that in here. So coordinates at pi over 6 are going to be 1/2 root 3 over 2. Coordinates at pi over 2 are going to be 0, 1. So that's pretty much that trig wheel that you'll see on every exam, including the final exam. This is just the portion we need. Now going back down here, sine squared of pi over 2, that's just going to give us a 1 squared for value 1. Sine squared at pi over 6. Well, at pi over 6, we get a root 3 over 2. We're squaring that one, so we'll get a 3/4. So we're integrating from 3/4 at the lower limit up to 1 at the upper limit. So it looks like everything is all set up. We're just going to change these last two with those values. Any last questions, folks, before we go to finish off this last integral here? Okay, so on the next step, let's take a look. First thing I want to do is give it a little bit of space. Pi over 6, pi over 2 are changing to 3/4 and 1. Now everything highlighted in blue is turning into this 1/2 du. The 1/2 we can put way in front of the integral. It doesn't have to be inside as a distraction. Du I'm going to put to the left to replace d theta. Now the sine power 4, that's the last thing remaining there, just turns into this u squared. So we have now 1 over u squared. So we did it, folks. This is now a problem that you would have seen in section 5.3. And the one up above, that's the nasty one that we had to transform in some way to bring it down to a section 5.3 problem. In fact, it's solved in pretty much the same exact way as well. We're going to write this as 1/2 from 3/4 to 1. We need to make a correction here. Anyone volunteers for a better way to write 1 over u squared? Exactly. For finding an antiderivative, this should really be the thing we're looking at. It's not as if you can't get an antiderivative here, but the things you do to the numbers are different if your u is in a denominator. You have to learn a different strategy. It's much easier to learn this if you always force u to be in the numerator. Now the exponent's going to go up by 1, whereas here it would have gone down by 1, and that's just way too confusing to even deal with sometimes. So let's keep it this way. Next step, I'll copy in the constant of 1/2. Give it a little bit of space and write down the base of u. The power goes up by 1, so -2, add 1 to it for a power -1. That means we're dividing by -1. And I'll take just that one piece, u power -1, and we'll evaluate it from 3/4 to 1. So that's our next step. We found an antiderivative. Now we're evaluating it with that bracket there. On the evaluation steps, we're now looking at -1/2. And let's see, let's call this 1 over u for just one additional step. It's kind of funny, for antiderivatives, I like the negative exponent because u is in the numerator. But for evaluation, I think it's better to bring it back down to the denominator, force the exponent positive. So now next step, we have -1/2. I'm plugging 1 in first, so it's just a 1 over 1. Minus goes here, then plug in 3/4. This is 1 divided by 3/4. That means we're putting in 4/3, the reciprocal. Does that make sense, folks, on that step so far? Okay, so we have 1 minus 4/3. We're at the arithmetic portion of this. That's as good as 3/3 minus 4/3. So we have -1/2 multiplying negative 1/3. We're almost there. These multiply together and return to exactly 1/6 on this problem here. So the area under the curve of cosine theta sine cube theta, as we go from pi/6 to pi/2, must be that quantity exactly, not a bit more or less. We did it, folks. I think that's a pretty awesome substitution on this one. There's lots of ways to make this work. So if you tried something different, you might have a whole brand new solution to get that would work just as well. Any other questions at all in getting through this one? Yeah.
So if you put cosine and then take your use that as your u, and it would work out also.
You know what, with cosine, I think that one might be a little bit problematic on this one. Let's give it another try just to see what would happen. This is honestly the best way to learn U substitution. You just have to try stuff and just see what happens. You have to play around with it and see what sticks. And with that particular substitution, let's take a look. If we set u equals cosine, then the differential here will be du equals, oh, let me use the same colors as usual. Du for the differential will be negative sine theta d theta. And let's see, if we went with this route, we would need to put sine theta into the numerator again. The cosine theta would turn into the u. I think it would probably work out. It might be a little bit trickier on this one. Another one to try would be potentially u equals sine theta. And it's kind of curious. This one's a struggle because we have negative sine theta d theta. There's no sine in the numerator, and multiplying by sine over sine is probably going to be more algebra on this one. If you let u be sine theta, the differential will be du equals cosine theta d theta. And I think this approach is actually the easiest one. With cosine theta d theta, you can fully just rip that out right here. There's no extra things to multiply or divide by. This portion will turn into a u cubed instead of just a u. And then the whole problem is just pretty much over at that stage. What's strange is with a wildly different substitution, it will still give you the right value as long as that substitution does work. Other questions about that so far? Okay. Yeah, it is kind of wild. Sometimes people pick substitutions that just seem like they are completely out of left field and they end up working. And sometimes they end up working better than what might have been a natural choice. These are pretty wild problems sometimes. But I guess I'd have one question for the class. Should we try one more, or are we feeling okay about this? One more? Good call. Let's try one more. So next problem, let's see. Let's go with integrate from 1 to 4, 3 to the power of root x divided by root x dx. So what that made the last problem kind of tricky is it's not easy to see what's an inner function in all this mess right here. But on this problem, there's an exponential with a square root function thrown inside. I think for this problem, it's a natural choice to try u equals square root of x and just see what happens on that choice there. So let's run with that and hope for the best. If you differentiate root x, you just get 1 over 2 root x. So the differential goes du equals 1 over 2 root x dx. So with that differential there, notice there is a root x dx. We're on the right track. We just don't have the constant 2. There's always a good fix if you're only off by a constant. Just eliminate it, multiply both sides by 2. We have twice du is 1 over root x dx. That means everything is all set up on this one. If you can spot an inner function, usually that's a good choice for a substitution. Here, it wasn't clear that the best inner function was sine theta. These ones are a lot trickier, I think. Well, next thing we want to do is take our upper limit. The upper limit is operating with a variable x, so we write x equals 4. Lower limit is x equals 1. When we transform them to u, we write out this way. It's taking the square root of both of those limits. So 4 goes here, 1 goes there. And now those are the new values for u. Take the root of 4 to get a 2, the root of 1 to get 1. And now everything inside this entire problem can finally be replaced. Any questions at all, folks, before we run through the rest of this one? Okay, let's give it a try. We're integrating from lower limit of 1 to an upper limit of 2. Our problem is 3 to the power of root x. That would turn into 3 to the power of u through that substitution right here. Next, root x dx, 1 over root x dx. That's all of this right here. That's just going to turn into 2 du. I'll put the 2 out here so it's not a distraction, and du right here. At this stage, it's just an ordinary antiderivative, but these kinds of functions are definitely tricky. We don't do these kinds of antiderivatives terribly often. Anyone happen to remember how it would go? If you're not sure, that's okay. Let's put this on the notes right away. And the best way to do it, antiderivative formula, is start with a differentiation formula, because that's important too. So it would go like this. The derivative with respect to x of 3 root x is 3 root x times the natural log of the base. The base was 3, so we take natural log 3. This means the antiderivative, notice this one's an indefinite integral. We don't have limits of integration for 3 root x dx. Antiderivative means we're doing this formula backwards. You get 3 root x still. Instead of multiplying by root 3, you divide by root 3. Natural log 3, not the root. Then add a constant, and that's a formula for the antiderivative of this thing. That means back over here, we just cite the formula. We're taking the simplest antiderivative, so we won't use the constant c, but it has to be there as a formula. I write this all in as 2 times 3 to the power of u, divide by this natural log 3. I'll put it out in front this way. And this portion, we evaluate from 1 to 2, leaving the 2 natural log 3 factored out as we evaluate. Does that look all right to folks on getting that antiderivative? Okay, so after we get to this stage, we are pretty much home free. The methods are write out 2 natural log 3. We're putting in 2 to start, so it's 3 squared minus 3 to the power 1. But this is just 9 minus 3, so we get a value of 6 here. So altogether, it looks like we're dealing with a 12 divided by natural log of 3. And it doesn't simplify any further on that. We've got it, folks. This one's not bad in some senses, but it's nasty in other senses. The antiderivative is tricky, which is what was terrible on this one. Whereas on this problem, this one's tough because it's hard to start and find the right substitution to get through on it. Well, any last questions, folks, on these problems here? Okay, so that's finally the substitution rule. We'll have more opportunities to practice this in the coming sections that we're taking a look at. But we also made one other promise before we went on break, Thursday, which feels like a long time ago already. We want to take a look at just a really fast extra concept. The ideas of even functions versus odd functions. Sometimes, I'm probably not going to put a trick question like this on a real final exam, but you might see occasionally something that looks really, really hard to integrate, like that thing, and none of our methods work. There's no good u substitution for this thing. You wouldn't want to use integration by parts on this necessarily, but we can still calculate this in one step. The thing that we need to make that happen is just a review on symmetry, even versus odd. So here's a really quick review. This isn't so much calculus, but it's about to turn into it when we see the new formulas. First thing to talk about is the so-called even function. An even function has symmetry with respect to the y-axis. That's what makes it even, but also satisfies this equation. F at negative x turns into f of x. Visualizing it, this is what it would look like. F at a negative 0.5 gives us this value, and so does f at positive 0.5. If I draw these just right, sorry, shaking hand, that looks a little bit off. So you have this property right here. And honestly, a good way to remember you have an even function is through this example. F of x equals x squared is an even function. But so is this. F of x equals cosine x is also even. And you can check cosine of negative x is always cosine x. So that's a nice fact about the cosine function. Turning down to odd functions, same kind of idea. You'll know your function is odd because you have symmetry with respect to the origin. That means this point right here, it flips around the y-axis for the first reflection and lands somewhere about here. Then it flips around the x-axis for another reflection and it ends down here if I drew them perfectly. Pretend that was there all along. That's what symmetry about the origin means. It means the only point that doesn't change is that one, the one that goes through the origin. So nice functions that have odd symmetry would be this one. Power 3 is odd, so that makes sense. It ought to be an odd function. I'm assuming that's how the naming scheme was invented. And for an additional example, take a look at this function. F of x equals sine x is also odd. And that means as a consequence, sine of negative x equals negative sine x. So this formula here came from that information. And likewise for this formula, came from the fact that we had an odd function, or excuse me, an even function. So it came from that equation above. So you might say, so what? What does even and odd functions do or help us with integration? But here's the visualization for us. Suppose you were going to integrate from, let's say, -1 to +1, x to the power 3 dx. Now we can go through the ordinary motions, find an antiderivative, evaluate it, and all that kind of stuff. But we're looking at the picture right here. If you're integrating from -1 to +1, f of x is x cubed, that is this graph, you're first going to pick up all of this area. That's all negative area now. And then you'll pick up all of this area. All this area is positive, but the function was also symmetric. Symmetry means this negative area is exact in quantity, other than the sign, to this positive area. It balances to 0 and the integration is over immediately right at that step. That's kind of the nicest way to ever evaluate an integral. If you ever notice that in an exam, then that's the answer. Any questions, folks, with the rundown with even and odd functions? Okay, so sometimes symmetry is helpful because if we have symmetry, our areas are also symmetric if we're integrating on the right range. So let's turn to this function, or this last concept here. If you are dealing with an even function, it's not as fantastic. If you're going from -a to +a, you could just go from 0 to a and double the answer. The visualization of that would be, say, if you're integrating from here to here, you really just have to integrate from 0 to 1, double that area, and you have the whole integral because of symmetry. The second portion is saying, if it's an odd function, and you integrate from a -a to a +a, you just get a 0 out. And that's what we were looking at on this example here. That's fantastic because now you don't have to solve any integral. The answer is, well, it's still hidden by the fact it's an odd function, but it's there. So let's try this out with example 4. We want to determine first if x power 4 sine x is even or odd. And that's honestly kind of tricky. Here's a strategy for doing that sort of thing. You want to compare f of negative x with negative f of x. So this would always be the first step of deciding if you have an even or odd function. We could plot the thing, but graphs are just really deceptive for this sort of thing. It's better to know once and for all algebraically, so a graph doesn't trick our eyes. So f at negative x means we're placing negative x here where x power 4 is. We're also placing it here where sine x is. We can evaluate negative x power 4 pretty easily. That's just going to turn into positive x power 4. The even exponent wipes out the sign. But over here, something extra happens. Let's turn up above. Sine is an odd function, so sine of negative x will turn into negative sine x. So this whole thing turns into negative x power 4 sine x after simplifying. Any questions so far, folks, on this line here? Okay, next thing to do is negative f of x. That one's not so bad. All we're doing is taking the f of x function up here, multiplying it by negative 1, and we get negative x power 4 sine x. Next, we make a comparison. We have that f of negative x came as negative x power 4 sine x, and so did negative f of x. So we're ready for a conclusion. We'll say, therefore, f of negative x equals negative f of x. Let's scroll up on the notes just for a reminder. If this ever happens, that's much like what happened here in green, and that's the definition of an odd function. The negative inside the function as an input turned into a multiplication factor. We saw that happen down here, and so we're going to conclude f of x is odd. That absolutely deserves an exclamation mark, because if you have an odd function and the domain you're integrating across is symmetric, negative pi over 4 to positive pi over 4, then the problem is over. It's 0, and there's no need to try to find an antiderivative of that thing. That one would be really hard to get through. Well, that was the additional topic that I promised we would take a look at. Any questions at all, folks, on finishing this one here? Okay, well, we're now complete with the section 5.4 notes. I think it was definitely worth getting that extra practice in. And with where we're at so far, we're taking a look at section 6.1. I feel like I got a little overexcited on this assignment. I might have to take off the 6.2 right here. There'll still be problems to solve to prepare for the final exam, but I'm going to post the solutions to all of those so that you'll know what the solutions are. I'm going to make the assignment number 14 just settle around section 6.1. Well, any other questions so far, folks, with the end of these notes here? Okay, well, we are now currently in section 6.1, areas between curves. These notes aren't terrible to get through, but it takes some time to describe what we're doing. They'll feel awful familiar once we get far enough along. We're going to describe the method of finding areas between any curve to start off. My reminder will be we're dealing with the fundamental theorem of calculus part 2. So we're going to turn the problem into a definite integral right away. And we'll solve these kinds of problems. But honestly, they're really not too bad. We don't have enough time to go through one in full, but I want to just leave you with this last thought. If you're trying to find this area, and it's between two curves, really all you're doing is taking area is a definite integral from starts at 0, goes up to 2. We put the larger curve first, subtract the lower curve after that, and then we just solve that integral right there. So that's the essence of section 6.1. We're going to solve this problem in full when we come back on Thursday's class tomorrow, so we'll come back to this one. But I just wanted to show this just as a reminder that the purpose of chapter 6 is just so we can get more practice with integration, really. And like we see here, that's exactly what we're going to be doing. Just practice integrating some more to finish out the course. Any questions at all, folks, before we call tonight a little bit early today? Okay, well, so call it tonight a little bit early. If you have questions, I'll be happy to help after class, I guess right now. And when we come back on Thursday, we'll take a look at these notes. That way we're not breaking the concept in half or breaking a problem in half. Well, have a great day, folks, and I'll be happy to help out if you have any questions.